All right, today we're going to get into something really cool, and honestly, sometimes a little frustrating in the world of chemistry, how you actually build molecules. When chemists are making these complex drugs or new materials, they're basically like molecular architects, and they need absolute, total precision. So, how on earth do they pull that off? Let's get into it.
Okay, so just think about this for a second. How do you build anything complex, piece by piece, without messing up the parts you've already finished? It's a huge challenge, right? Whether you're, I don't know, gluing together a tiny, delicate model ship, or you're literally building with atoms. Well, for a painter, the answer is super simple. Painter's tape. I mean, if you want to paint the trim in a room, but you don't want to get paint all over the walls, you don't just, try to have a super steady hand. No way. You use a tool. You mask off the areas you want to keep clean. It's such a simple but brilliant solution.
And that is the big idea we're going to unpack today. Because chemists have come up with a very similar strategy, a kind of temporary mask for molecules that lets them work with just incredible precision.
Okay, so let's start by digging into the problem this molecular tape is supposed to solve. I mean, why is this even necessary? Why is it so important in chemistry?
Well, see, most of the molecules that are actually useful, like medicines, they're not just simple little blobs. They've got all these different parts, what chemists call functional groups. Some parts might be an alcohol, others are amines, and they all react differently. It's just like a room, right? You've got your walls, your trim, your windows, all different surfaces that need different kinds of treatment.
And that is the million-dollar question, isn't it? What if you need to chemically tweak the trim of your molecule, but you absolutely have to leave the walls and the windows completely untouched? I mean, if you just throw your chemical paint at the whole thing, it's going to react everywhere it can. You'll just get a total mess. You need control.
All right, so if that's the problem, what's the solution? Let's take a closer look at how this molecular painter's tape actually gets the job done.
So at its heart, a protecting group is just a molecule you stick on purpose, to block a specific reactive spot. Think of it as a temporary shield. You put it on, and it basically makes that part of the molecule invisible and inert to any other chemicals you throw in.
And the whole strategy follows this really beautiful, logical three-step process. It's like a little dance. Step 1, you protect. You put the tape on. Step 2, you react. You go ahead and paint the exposed trim. And step 3, you deprotect. You peel that tape off the wall, and boom, a perfect, clean, sharp line. It's this awesome cycle of mask, modify, and then unmask.
Now this all sounds perfect, doesn't it? A flawless solution to a tricky problem. But in the real world, chemists have this kind of love-hate relationship with protecting groups. They're often seen as, well, a necessary evil.
This quote right here really nails the feeling in the chemistry community. So why the sad fact? Why aren't they just celebrated? Well, because adding and then removing these groups means adding extra steps to your process. And every extra step costs time, it costs money, and it can lower the amount of the final product you actually get. Every single step is another chance for something to go wrong.
Yeah, choosing the right protecting group is not simple at all. It's a really delicate balancing act, as you can see here. Chemists have to ask themselves all these questions. Will the tape stick only where I want it to? Will it peel off cleanly later without ripping the paint underneath? And is it tough enough to survive all the other steps I'm going to do? Get any one of these wrong, and your whole project can just fall apart.
So, because of all these very specific demands, chemists have developed this huge, diverse toolbox of different protecting groups. Each one is basically custom-made for a specific job.
And this table here really shows that there is no one-size-fits-all solution. Nope. The tape you'd use for an alcohol is totally different from the one you'd use for an amine. And each of these crazy acronyms, like BOC or TBDMS, they represent a very specific molecular structure, each designed with unique properties. It's best to think of them like different brands of painter's tape. Some are for delicate surfaces, others are super heavy-duty.
To really get a feel for this, let's just zoom in on one really popular class of these things, used for alcohols. They're called silly ethers. The key thing to understand here is that even within one family of tape, you can get all these different levels of, well, stickiness. Okay, this chart is just fantastic. Just look at that staggering difference. Under the same acidic conditions, the TMS group on the left comes off 5 million times faster than the TBDPS group on the right. 5 million. That gives a chemist unbelievable control.
Do you need a piece of tape that comes off with just a gentle tug? Use TMS. Do you need tape that's going to survive a hurricane? You go for TBDPS. It's this tunability that makes these tools so incredibly powerful.
So, we've seen that using protecting groups is a super clever but also pretty complicated strategy. And that brings us to the highest level of thinking in this field. What's the ultimate goal here?
And there it is. This is the absolute pinnacle of chemical elegance. The most celebrated molecular architects, they aren't just masters at using the tape. They're the ones who can figure out how to do the whole job without needing any tape at all.
And doing that requires this just profound understanding of how molecules react. It's all about designing your sequence of reactions so cleverly that your chemicals only go to the exact spot you want them to, just naturally. It's like the chemical version of painting the trim with one single, perfect brushstroke, no tape required. It's beautiful, it's efficient, and man, is it difficult to do. So, while this molecular painter's tape is one of the most essential tools in any modern chemist's toolbox, the real dream, the ultimate goal, is to build a world where you don't even need it. A world of perfect built-in selectivity. Is that future even possible? Well, that's a question that drives innovation in labs all over the world every single day.